Everyone, welcome to BCP Med. In this video, we are going to be looking at the concept of electronegativity. We are going to be looking at how electronegativity is defined from bond energies, how the Pauling electronegativity scale works, and how electronegativity is related to bond polarity. Let's go ahead and get started. So, what is electronegativity and how is it defined? Well, electronegativity is a measure of how much atoms pull on electron density in a chemical bond. And the difference in electronegativity between two elements tells us how polar a bond is going to be. But where do the numbers come from for the electronegativity scale? Well, electronegativity is a relative scale, meaning it just serves to compare two atoms, say X and Y. And specifically, it's going to compare the bond energy of the diatomic molecule XY. Specifically, what we're going to do is we're going to compare the bond strength between the atoms X and Y, measured in kilojoules, to the energy of the bonds between two XX atoms to themselves and two Y atoms to themselves. We can represent that information through the following equation, which is a little bit complicated, but we're going to break it down. The term on the left gives us the electronegativity difference between two atoms, X and Y. Now, this term here is going to be the geometric mean of the bond energies of X and Y, respectively. So this energy here is the bond energy of the molecule XX, the diatomic molecule. This energy here is the bond energy of the molecule YY, and so this is the mean. This is the average energy of these two molecules. This here is the bond energy of this molecule here, XY, as measured experimentally. So what this equation is really saying here is that the electronegativity difference between X and Y is the difference between the bond energy of XY and the average bond energy of XX and YY. How does this get us to the idea that electronegativity is a measure of bond polarity, that it has to do with electron withdrawing ability? Well, as we know, ionic bonds are stronger than covalent bonds, right? And this is because of the stronger electrostatic force between charged species. Therefore, more polar covalent bonds with more ionic character, are going to be stronger than non-polar covalent bonds, right? Any homonuclear bond between the same atoms, like XX here, or YY here, is going to be completely non-polar. As such, if a bond between XY is stronger than either of these, or rather stronger than the average of these two, it is necessarily going to be more polar. And so this equation, which tells us the difference in bond energies between these, is also in effect giving us a measure of how much more polar this bond is than these two, right? We know these are 0, and so this is an effective measure of the absolute bond polarity of the XY bond. But again, this is a relative scale, right? We're only talking in terms of the electronegativity difference with this equation. So we need to go ahead and assign, well, first off, right, the phrasing, how well an atom in a bond pulls electron density towards itself, comes from this expression, right? The polarity of this equation. And so we need to go ahead and assign a absolute scale. So we're going to go ahead and define fluorine as arbitrarily being a 4 on the Pauling electronegativity scale, so that we know now one of these values is going to be a 4, and we can define everything else based on that. So let's go ahead and look at a simple calculation to get our feet a little bit more wet. Let's calculate the electronegativity difference of HCl using our bond energy equation. To do this, we're going to need some bond energies. The values we need are going to be shown here on the left. The HH diatomic bond is at about 432 kilojoules per mole, while the Cl-Cl bond is at about 239 kilojoules per mole. Meanwhile, the HCl bond clocks in at about 427 kilojoules per mole. Notice that this is larger than the average of the homonuclear bonds, right? The HCl bond is going to be stronger than the average of HH and Cl-Cl. This indicates that the HCl bond is going to be more ionic-like and more polar than either of those bonds. What we're going to do now is we're simply going to take our equation and we're going to plug in values. We're going to plug in the BeXY as the HCl bond, and then the XX and YY respectively as HH and Cl-Cl. And we're just going to use the kilojoules per mole conversion, and we're going to plug it in, and we're going to find out that H and Cl have an electronegativity difference of 0.96, right? This is not the absolute electronegativity value of either of these elements. This is their difference. And you might be wondering, well, does this match what you might know about the electronegativity values of H and Cl that you might have seen in a general chemistry class? Well, let's go ahead and find out. This periodic table that I've thrown up here has the electronegativity values of all the elements rounded to the 10th place. If we go ahead and look at H and Cl, their difference is indeed about 1, which is what we calculated based on our total bond energies. So we weren't totally making that up. Let's also go ahead and look at the periodic trend associated with electronegativity. We see that the electronegativity values increase from the left towards the right-hand side of the periodic table, mirroring the trend of effective nuclear charge. That makes sense because the effective nuclear charge tells you how tightly held the electrons are going to be onto the atom, and electronegativity tells you how hard an atom is pulling on electron density. So the two naturally go together. Now, we also see that electronegativity is going to correlate with atomic radius. As the atomic radius decreases going upwards on the table, the electronegativity is also going to increase upwards on the table. This is because the smaller the atom, the harder the nucleus is going to pull on the electron cloud, right? The electric force is an inverse square law, and so the closer the nucleus is to the electrons, the harder it pulls, the larger the electronegativity value, right? Fluorine has the highest Z effective and is also the smallest atom, ignoring helium, because it doesn't really bond, and so fluorine is going to have the highest electronegativity. On the other hand, alkali metals like cesium, which are very large due to having very many energy levels and having a very low effective nuclear charge, are going to have a very, very low electronegativity value of about 0.7, in fact, which is 3.3 units lower than fluorine. We can go ahead and see the physical reasons for these relations here on this slide. From the Coulomb equation for electric forces, we can see that the force one charge exerts on another is related to the magnitude of those charges. Since electron charges are all the same, the only charge that varies is the nuclear charge, which we've circled here as Q1. The larger Q1 is, the larger the pulling force on the electrons. We can see this diagrammed out below. The nucleus with the +1 effective charge is going to pull much less on the electron cloud than the +7 nuclei, as indicated by the thickness of the purple arrows. As a result, the top nuclei will be less electronegative because it's less withdrawing towards electron density. Similarly, the radius also affects the pulling force, right? As you can see here, the force is inversely related to the radius squared. As a result, the larger an atom gets, the less electronegative it will be. And again, you can see this diagram below as given the two radii, little r and big R, for the same nuclear charge, the little r is going to have the thicker arrow, the stronger pulling force on that electron cloud as compared to the big R, right, which has that thin arrow. And that means that the smaller radii atom is going to be more electronegative because it pulls harder on that electron density. Now, electronegativity is an extremely important qualitative measure for chemical analysis because a rough definition of bond polarity is often written in terms of electronegativity difference. Remember from our discussion of bond energies that electronegativity differences really measure how ionic-like a bond is based on how strong it is relative to the bonds of the composing elements, those diatomic bonds XX and YY. As a result, a bond with a small electronegativity difference between X and Y is going to be similar to the nonpolar bonds of XX and YY, meaning the XY bond is also going to be relatively nonpolar. A bond with an electronegativity difference of less than 0.5 is typically considered the cutoff for a nonpolar bond. And a classic example of that is the CH bond, which has an electronegativity difference of 0.3 between the elements. A polar bond, on the other hand, is one that has an appreciably larger electronegativity difference at somewhere between 0.5 and 2, and that's going to have an XY bond, which is considerably stronger than either XX or YY. Or rather, the average of XX and YY, to be more precise. And a classic example of that is going to be the HCl molecule, which has a difference of about 1 between the constituent elements. Finally, an electronegativity difference of greater than 2 is going to be considered an ionic bond, and that's really only seen between metals and nonmetals, such as sodium and chlorine, for example, which have a difference of about 2.2 between them. To close off here, I want to go ahead and show you a tool to visualize electronegativity in molecules. These are known as electrostatic potential maps, and they show the relative distribution of electron density over the volume of a given molecule. Red indicates regions of high electron density, or negative electric potential. On the other hand, blue represents regions of low electron density, or positive electric potential. So, because electronegativity is directly related to how much atoms pull electron density towards themselves, red areas can also be said to represent atoms with high electronegativities, and blue areas represent lower electronegativity atoms. Clearly, in this molecule, the 3 fluorine atoms are going to pull the electron density towards themselves, and indeed, they are going to be dark red, indicating that they carry partial negative charges on this molecule. On the other hand, H, which is very small and has a low electronegativity, is going to be blue, indicating that it has a low electron density. It is going to be electron deficient and carry a partial positive charge in this molecule. These tools can be very helpful in understanding the behavior of larger molecules and will often be used to show why a certain functional group behaves the way that it does. And with that discussion of potential maps, we've actually reached the end of our content for this video. Thank you guys so much for watching, and if you enjoyed what you saw, please go ahead and like and subscribe to the channel. Make sure to check out our other videos in the chemistry playlist to learn more, and if you're looking to branch out a little bit, check out our other science playlists as well. See you next time.